This was where we started last time, pretty much. This is the temperature axis, this is the pressure axis, and if you cool down a gas, the pressure comes down, and then ultimately, if you can keep it in a gaseous state, then this line would intercept the temperature axis, and this is at minus 273.15 degrees Celsius, which sets the Kelvin scale. So the Kelvin scale of temperature, the absolute temperature, so it's called Kelvin scale or absolute temperature scale, is now defined as this 0 here. And that's the one we use when we do calculations in thermodynamics, which is what we are basically doing right now. So the basic idea then is that we have a temperature scale, which is this Kelvin scale, if you will, and this Kelvin scale temperature would be the Tc plus 273.15. And that's important because that's the natural scale that we have. That's the scale that nature gives us. It's not an invented scale like Celsius or Fahrenheit and so on, which were done by us under fairly arbitrary circumstances. This is what nature tells us is an absolute 0 of temperature, and you can't go beyond that. You can't go below that. All right. So the important thing is that to keep in mind that most, if not all, calculations in heat and what we call thermodynamics, which we haven't really done, we'll touch upon that a little bit today, requires temperature to be expressed in the Kelvin scale. So be careful about that. If I tell you that some temperature measurement is needed, that should be ideally expressed in Kelvin scale. Where you don't necessarily need to express something in Kelvin scale would be if you're interested in the difference between two temperatures. Then you don't need to express, right? Because the difference between two temperatures would be the same, regardless of whether you are using using Celsius or Kelvin. All right. So having said that, let me move on to what happens to solids, liquids, and gases when temperature goes up or goes down. Now this is of great practical importance because much of our world around us is very, very sensitive to temperature changes. So how do solids, liquids, and gases, let's say the three states of matter, three most common states of matter, well, I'm not even sure if these are most common states of matter. That's the question. How does it change with temperature? So one of the things we'll look at is thermal expansion and thermal contraction. And here, for example, suppose I have a bar. Let's say a metal bar, and the metal bar has some length L0. Okay. And correspondingly, I can have some kind of a volume here, and let's say this volume is V0. So let's say L0 cubed or something, and it's V0. Okay. So, and let us say this is at some temperature T0. Whatever the temperature is, doesn't matter. Suppose now I raise the temperature, so I make it into T0 plus delta T, where delta T is a small temperature change. It can be up or down. Okay? So now what happens is you find that this rod, let's say temperature has gone up, so delta T is positive. Depending upon the material, you will find the rod has become longer by an amount delta L. So basically we know from experience that when we heat a material, it can expand, and almost always they do. So same thing happens here. So if you change the temperature here to T plus delta T, this will be L0 plus delta L, and this could also ever so slightly expand to V0 plus delta V. So this now becomes V0 plus delta V, the expansion being delta V. Total length here obviously will be L0 plus delta. So how does this work? How do we express that? How do we calculate that? It's really very easy, because delta L, this expansion amount, depends upon two quantities. It depends upon the temperature change that has happened. So it depends upon how big or how small delta T is. So if delta T is quite a bit, expansion may be quite a bit. That's a general fact. Usually if you raise temperature, most things wouldn't contract. Mind you, I said most things, not everything, but most things wouldn't contract. Okay? It also depends upon how long this was to begin with. So delta L also depends upon L0. So if it was very long, then delta L might be quite a bit. If it was already very tiny, then delta L would be proportionately tiny. So therefore the absolute value of delta L would depend upon how long it was and what the temperature rise has been. And so you convert the two proportionalities into an equation, and the equation is this. This, by the way, is a proportionality, and this is an alpha. Okay? So alpha is the coefficient of linear expansion. So alpha here is called coefficient. So it's a constant for each material. So naturally, if I have aluminum, which responds to heat readily, expands readily, the alpha would be quite large, relatively speaking, for aluminum. On the other hand, if I have something like glass, which is more of an insulator, it doesn't conduct heat quite that easily, then alpha for glass would be smaller. Just the same way, delta of V, the volume, also turns out to be proportional to delta of T, and delta of V also turns out to be proportional to V0. So we can write a similar expression here. Delta V is equal to beta V0 delta T, where beta is what we call the coefficient of volume expansion. And typically you will find that 3 alpha is equal to beta most of the time. So let's look at some numbers to get a sense of how this alpha and beta, how these quantities are. Now I'll give you two materials here. So let's say we have the material here, and we look at quartz. Quartz is like sand or glass, and then we have aluminum. So we have alpha. Now if you look at the units of alpha, delta L should be a length. So this is a length. Here you have temperature. So you should have inverse temperature. Units of alpha should be inverse temperature, so that you get dimensionally balanced equation. So therefore it's 1 over Celsius or 1 over Kelvin. And similarly, you'll have beta as 1 over Kelvin as well. So for quartz, it turns out that the number is relatively small, 0.04 times 10 to the minus 5. And because beta is 3 times as much, so it's 0.12 times 10 to the minus 5. Okay? Correspondingly, for aluminum, which gets hot very easily, this number is many times larger, being 2.4 times 10 to the minus 5. So it's basically 1 over 100, and this is of the order of more than 1. So it's 2 orders of magnitude larger. And here it would be 7.2 times 10 to the minus 5. Okay? So these problems are obviously relatively simple. So for example, you may be asked that in summertime, you'll find that places that get pretty hot, the roads get very damaged during the summer heat. And what actually happens is that basically they expand. And you can, if you have any kind of metal present to hold the roads or to hold the concrete slabs in place, which is often the case in the interstates, what you find is that they actually tend to buckle because of expansion effects. And so one of the things that one does is when one lays down the concrete slabs or one lays down pieces of a roadway, there is a certain gap that is kept between 2 consecutive slabs. And that's where you will find some kind of metal. So when you go over a bridge, for example, you notice that your car makes a bit of noise as it goes over these slabs. And what these are regions that are kept empty such that for extremely hot climates, you can allow for expansion without actual damage to the road. So this is a simple example. Same thing happens in almost every sphere of our daily life. All right. I've already done phase change, but let me go over that quickly again because we haven't really spent a lot of time. I'll talk about some more material here. But let me quickly go over phase change because I have given you some phase change problems and I will also give you some phase change problems as we get into the finals. So the states of matter, the most common states of matter as temperature goes from high to low would be gas, liquid, and then solid. So here temperature is going down as we go to the right. That's what I mean by the symbol on the right. And one of the things that we discussed is that the gas to liquid transition that we see, this thing happens at the boiling point. We call it TB. And TB is the temperature at which you go from a gas phase to a liquid phase or alternatively from a liquid phase to a gas phase, depending upon which way you are going. And this would be the melting temperature, Tm. So these phase changes, by the way, are notoriously difficult to study. So essentially the problem is that when a system goes through a phase change, the system is kind of trying to decide what to do. It is in a very mixed up state because imagine a liquid is trying to freeze up and become a solid. When a liquid tries to freeze up and become a solid, it's not just one molecule, it's zillions of molecules that are running around in the liquid. And everybody must figure out what to do such that instead of pretty much floating around, which is what these molecules do in a liquid phase, they are going to sit in specific chairs, if you will, because every solid has some kind of structure. Even if it's somewhat disordered, they have some kind of typical structure. They have the molecules sit at certain distances to each other. Depending upon the nature of the material, the molecules may sit in very specific arrangements. There are a whole bunch of different kinds of lattices that each and every substance, when in solid phase, may or may not take. Glass, for example, is a very disordered liquid. So all these things are happening. Some of you are playing with a phone. So if you think that I am not seeing, you are dead wrong. So the deal, therefore, is that these guys have to cooperatively figure out what to do. And imagine, these are not human beings, these are actual molecules that are interacting with each other, and over enormous distances, across relatively short times, they are figuring out what to do and where to sit down. And this is actually what happens when you go through something like the freezing or a melting process, depending upon if you go from liquid to solid or solid to liquid. So as you can imagine, it's an extremely complex process the dynamical behavior of which we actually, even to this day, don't understand, which is the reason why, for us to predict melting properties and freezing properties, as long as they are in equilibrium, it's more or less manageable, but when the thing is actually happening, it is actually very difficult to predict. And we don't really have a very good theory that describes it even to this day in 2018. So these processes, therefore, actually, they may seem perfectly ordinary, but they're extremely complex. Now, you may wonder, why do we really care as to how these molecules move? But let me give you a simple example. The reason why we care is because if we want to make a material that's very, very heat resistant, how do you think we'll make it if we don't understand how these materials behave when they are really hot? To understand that, these phase change physics is very important. Okay? In fact, I can tell you that we don't have materials that are very good at very high temperatures, which is why people talk about geothermal energy, getting energy from the ground, because there is magma, there is this, there is that. But the fact is, it doesn't really work, because most of the materials, in fact, all the materials that we have, if you stick it in the ground, there is a reasonable amount of geothermal energy, the thing is going to melt. And that's the end of the story. There's nothing you can do. Okay? If you go to Yellowstone, the entire Yellowstone is sitting on a caldera. It's actually one of the super volcanoes of the world. The last explosion was something like 60,000 years ago, so we are headed towards another explosion, at which point most of us won't live anymore and Yellowstone explodes. Now, the thing is that if you want to generate energy out of the heat in the Yellowstone, it's a fantastic source, but we have no material that can pretty much poke into Yellowstone more than a few feet. They all melt. Okay? So high temperature materials are very important. Same for very, very low temperature materials, but high temperature becomes a real issue, and we are still struggling as a science and engineering community to deal with materials that can survive and that can withstand very high temperatures. In fact, for our own survival, if you will. Why do you think we lost the Challenger crew? Because the Challenger crew, some years ago, when the Challenger burnt up while entering the Earth, essentially had a heat tile that fell off the Challenger spaceship. And these heat tiles are literally like bricks. They're thin tiles that go on top of the surface. And one heat tile falls off basically means that your heat insulation on the surface is gone, and the crew didn't know. So as they were entering the Earth, it overheated, and the whole thing basically blew up in no time. But if we had good material, that wouldn't have happened. So this is just an example, because temperature gets up to several thousand degrees Kelvin, and we simply don't have much protection when we get up to such temperatures. Now, one of the things I pointed out as you do these calculations is that when you are in a given phase, let's say in the gas phase, in the liquid phase, or in the solid phase, the equation that you have to think about to understand how much heat enters or leaves the system typically goes like delta Q equals some specific heat capacity delta T. So in each of these phases, you have this delta Q equals C delta T, and delta Q equals C delta T. And of course, if you have n amount of material, there'll be an m here. So that would be the amount of heat that the system would absorb or reject due to temperature change in any of these given phases. So this is something we can do. We can know the specific heat here, we can know the specific heat here, we can know the specific heat here, and we can do such calculations. However, when the system is going through from gas phase to liquid phase or from liquid phase to solid phase, that entire transition occurs at a fixed temperature. Right? So entire transition occurs at a fixed temperature means you don't have a delta T. So this formula clearly would not work, obviously, right? Because you don't really have a delta T. So if you don't have a delta T, what happens? So during phase change, what happens is that the amount of heat that goes in, let's say, is certainly proportional to the mass, but depending upon what's occurring, there is another constant, and this is, in this case, latent heat of fusion, that comes in at the melting temperature. So I think I gave you guys one problem, problem 7, in the homework set on this. And the reason why I gave it to you is because I'm going to be asking such questions in the final exam. So make sure that you do them if you haven't already, and I don't think you have. So that's why I'm pointing out that you better get it done. So this is latent heat of fusion. Latent heat of fusion would be here, and over here you have another quantity which is MLV, and that would be latent heat of vaporization. And this happens at T equal to T. So let's go through this then very quickly. So suppose you take a solid, okay? You take a solid here and you are raising the temperature. So suppose the solid is at some temperature T1 and it goes from that temperature to melting temperature. So T1 to T melting, in that window, the amount of heat involved, the amount of heat that the solid will absorb, will be dictated by this formula. Because this formula tells you as you change the temperature, if you know the specific heat in the solid phase, you can calculate delta Q, knowing mass. That's what it tells you. Now the solid melts and becomes a liquid. So two things you got to remember. First, as it melts, it goes through this kind of a process where the temperature is no longer changing, but it's still absorbing heat as it goes from a solid phase fully to a liquid phase. So therefore now you use this formula, which is telling you how much Q the solid would absorb as it heats up and melts, given its mass and given the nature of the quantity involved, which is the latent heat of fusion for that material. Let's say the material is iron. So then you look up the latent heat of fusion of iron. And then from the melting point of iron up until the boiling point of iron, when iron is going to basically become a liquid, a gas I mean, you will have a temperature range, at which point the heat absorbed, delta Q, would be C delta T M again, where you now use the specific heat value needed in the liquid phase. And now it goes to the boiling point. And here, you have to again not change temperature and give the amount of heat from this relationship, which gives you Q equals NLV. So once you know LV, once you know M, you can calculate the Q involved as it goes from the liquid phase and changes phase to the gas phase. And once it becomes a gas, depending upon what gas temperature you want, again you use the same relationship here, excepting now you use the specific heat in gas phase. So these relationships, these calculations are to be done in pieces. You need to know what goes where. And it is that specific understanding that I'm looking for from you when I ask you to solve a problem. So this is not rocket science, it's very simple, but you have to be clear that these C's in different phases are different. This is what you use when you go for a temperature change in phase, and this is what you use when you go for changes of phase itself, and they are different. Too many of you screw this up, so please don't do that. Any questions? Okay. So this is easy stuff. You shouldn't have problem. You have done far more difficult things already compared to this business. I think did I put up a table of hydrogen and water, the various specific heats? I think I did last time, didn't I? No? Are you sure? I thought I did. Anyway, I'll put it up again. So this is not something I want you to memorize, but just to give you an example of what's involved. So if you have material like hydrogen, for example, which we mostly see as a gas, the melting point of hydrogen, so this is where it goes from solid hydrogen to liquid hydrogen, or vice versa, liquid hydrogen to solid hydrogen. This occurs at 13.84 degrees Kelvin. So obviously at a very, very cold temperature. So this is minus 259.31 degrees Celsius. In other words, if you're outside the Earth's atmosphere where the temperature is 3 degrees Kelvin or so, and if you have hydrogen hanging around, that will become a solid block of hydrogen almost immediately. All right, so if you, the latent heat of fusion here, so the latent heat of fusion for hydrogen would be 58.6. So these are numbers to give you an idea. Times 10 to the 3 joules per degrees kilogram. Okay. The boiling point of hydrogen, so this is where the hydrogen would go from a liquid to our familiar form of being a gas, is 20.26 degrees Kelvin, so it's very cold. So that would be minus 252.89 degrees Celsius. So as you can see, the solid phase of hydrogen is more stable. The liquid phase of hydrogen is over the relatively short window of temperature, about 7 degrees or so, less than 7 degrees. And then hydrogen becomes a gas, and the latent heat of vaporization, so this is liquid to gas, and this is solid to liquid. So this is fusion, solid to solid liquid. So this becomes much larger. Hydrogen can actually suck in a lot of heat as a gas, and it's 10 to the 3 joules per kilogram. So as you can see, that hydrogen is a very important gas for us. We have a lot of hydrogen in our atmosphere, and one thing hydrogen does is hydrogen can hold a lot of energy, because 1 kilogram of hydrogen can essentially hold a great deal of energy, being something that requires that much energy to go to the gas phase itself. Water, on the other hand, is also very interesting. That's basically what is responsible for life itself. You can't have life without water, as far as we know. And here, the solid to liquid is 273.15. Or 0 degrees Celsius. So this is, of course, our normal 0 degrees Celsius temperature, where it becomes solid. For latent heat of fusion, to melt it, this is the amount of energy you need, 334 per kilogram, 334 times 10 to the 3 joules per kilogram. We all know that water boils at 100 degrees, so 373.15 Kelvin, so that would be 100 degrees Celsius here. And look at this, the amount of energy needed to convert solid to liquid, in this case, this is vapor, is this. So steam holds an enormous amount of energy. So these are just some comparatives, just to give you a sense of numbers that we end up dealing with when we talk about the amount of energy that is involved per kilogram as we go through various phase changes itself. And you can see that vaporization of water requires an enormous amount, but then even melting from ice to water becomes is also energetically not cheap, with 334,000 joules being taken up for just 1 kilogram of water to go from solid to liquid phase. Okay? So these are very important numbers in some sense, because it gives us an idea of how much heat is being absorbed by nature. And the fact that it's very difficult to do these calculations, we still, at this point in time, don't really have highly reliable ways of calculating how much heat exists in the atmosphere, and which is why there's always debate about not whether the Earth is warming, but how much the Earth is warming. And the fact is it's an impossibly difficult quantity to calculate because the Earth system itself is very complex. It's very dynamic. There's nothing really in equilibrium. These are all equilibrium numbers. So at the end of the day, these calculations almost become undoable. And the experiments, while they are probably most reliable, the fact is that they're also extremely expensive to do. And there is only some, there's always some risk involved in many of the experiments. For example, you can't measure very accurately the data for tornadoes and big storms because it's dangerous to do. It's not something that we find it easy to do, right? So, or we can't really figure out what kind of melting occurs or what kind of freezing occurs. I mean, these things again are expensive and sometimes very, very difficult to do, even they're being done completely remotely. The other thing that I want to touch upon today is the issue of heat flow. So this actually is a very interesting topic and rather useful for us also, just like this is. So heat flow can happen in three different ways. So one would be what we call conduction. This is typically the case for solids. Conduction. The other is convection, which is typically the case for heat flow in liquids and gases. So this is mostly in solids. Convection is mostly in liquids and gases. That doesn't mean that liquids don't conduct. Liquids do conduct, but the more important conduction problems are typically in the solid phase. So when we talk about conduction, we will primarily restrict ourselves to solid phase. So what do we mean by conduction? Conduction basically means that if I heat up, so suppose I have this rod, and if I heat up here, suppose I make this side, stick this side in an oven, what would be the temperature on this side? This is the kind of problems that we try to resolve in conduction. Okay? So as you can see, conduction is very important in building material with desired heat transport properties. If you want to make something which is an excellent conductor of heat, you want something in which whatever the temperature is here is very quickly becoming the temperature on the other side. On the other hand, you can also want whatever the temperature is here is not the temperature on this side. So the way we define conduction studies is by thinking about temperature at one end, let's say being higher than the temperature at the other end. So let's say temperature here is 10 degrees Celsius and temperature here is 100 degrees Celsius. So there is a 90 degrees Celsius temperature difference. Depending upon the material, how much heat will flow from the high end to the low end is what we have to figure out. That's typically a conduction problem. The third one that I'll touch upon is also very important, and that's radiation. For example, solar radiation. We all know that solar radiation causes damage to human DNA, as well as skin and everything else. So radiation basically is something that occurs in all media. Okay, so it also happens through vacuum. It doesn't need a medium at all, and I'll tell you more about it in a minute. So it happens in all of them, solids, liquids, and gases. Okay? So let's first go to the conduction problem. The conduction problem is actually, the way at least you guys need to figure it out, is quite straightforward. What we'll have is let's say one end at a certain temperature, the other end at a lower temperature. So let's say the temperature here is high. I'll call it T high. And this side is at T high, and this side is at T, what do I call it? T cold. Okay. Now I take a rod, let's say a metal rod or a glass rod or whatever, and connect the two. And say the rod is of length L. Okay? and the rod has a cross-sectional area A. So the cross-sectional area here is A. So it turns out that the heat flow, which is the amount of heat energy, so this is literally how fast the molecules are moving on the left side, being transferred, the energy being transferred to how fast the molecules are going to move on the right side. So when I talk about delta Q, it is that energy flowing in from left to right over some time delta T, and I call it the heat current. Let me call it H, and this H is something I'll call heat current. Delta Q, this Q, capital Q, is often reserved, almost always reserved, for amount of heat. Sorry. So this is the amount of heat that's able to flow from left to right, and primarily because we have a material there. Had the material not been there, that would have been done by air, and air does a very bad job of conducting heat by and large. So it turns out that the relationship that is experimentally found is like this. So it's inversely proportional to the length. So if the length is very large, the heat transport that occurs from left to right will be smaller. If the length is very small, heat transport will be larger. So that is not a surprise. Heat transport also will be affected by the cross-section. So if the cross-section is very wide, more heat is transported. If it's a very thin wire, then much smaller amount of heat will be transported. And it obviously depends upon the temperature difference between the two. But what is more important here is that this constant K that enters into the picture. And this constant K is the thermal conductivity. So as you can imagine, there is a great deal of research into making materials with the desired thermal conductivity. So we would like to be able to make materials that have the thermal conductivity that we would like for a very specific purpose. You can say, how can you do that? Nature makes the materials for us. So for example, if I take aluminum, or if I take some alloy like nickel and titanium alloy or whatever else, then you know that as you chemically make it, it will have a certain structure. So what control do you have other than mixing up and doing alchemy to figure out what material you get? The answer is that we have moved a lot since those times. So nowadays, you can grow a material that you want a lot of times. You can 3D print a material that you want. And this science is advancing very rapidly. So we are very quickly getting to a point where we can make a material that we know will have some desired properties. So we are actually able to get to a point in science and engineering where we actually can control this K and hence make new materials that would be very useful for desired heat conduction effects. Now just to give you a sense of these numbers, as you can see, the unit of this would be quite interesting. So let me give you this. The unit of K would be in watts. Watt is power, so that is joules per second per meter degree Kelvin. So that's the unit of this K. It turns out then that for silver, for example, which is a very good heat conductor, this K turns out to be 406 watts per meter degree Kelvin, whereas for a very poor heat conductor, one of them environmentally very unfriendly is styrofoam, which is almost not used except in possibly in McDonald's and some places. Environmentally very unfriendly, they shouldn't be doing it. Then this K is 0.01 W per meter degree Kelvin. That's just to make sure people don't get burnt easily by their coffee or whatever it is that they're having. But there are other material than styrofoam that's environmentally friendly. This one is not environmentally friendly at all. It does screw up our climate quite a bit. So that's just to give you a sense of numbers. So we have therefore discussed the idea of conduction, and I might give you some very simple problems, but you need to look up some of the worked exercises. We are getting to a point where I don't have enough time to actually give you exercises to work with before the final exams. Thermal conduction is actually one of the easier ones. Convection turns out to be quite difficult. Convection, by the way, plays a huge role in our weather, right? Because we know for a fact that ground can be warm, water surface can be cold, and hot air and cold air motion is controlled by such things. Hot air being lighter, cold air being heavier. So let's take a simple case. Let's take some liquid. In a container. Okay, some liquid here. And let's say that we heat this liquid from below somehow. And so as we heat this liquid, you would expect then that in the lower part of this container, the liquid is becoming hotter, right? Because it's getting heat directly from the flame. So as it becomes hotter, hotter means that the atoms and molecules will be moving with more energy. And as they move with more energy, they tend to be less densely packed with each other, which means that the liquid becomes lighter. So being hotter means it becomes lighter. But lighter than what? Lighter than stuff that's sitting in the upper layers, if you will, because that's more removed from the heat. So this one will be cooler. So the upper layer would be cooler and hence heavier than the hotter layer below. So as you can see, applying this heat should cause some motion, because something that is light would like to rise up and something that is hot would like to come down. And what happens is that the light stuff stabilizes into rising up like this, whereas the heavy stuff comes down like that to take the place of the hotter liquid that is vacating the area near the flame and trying to go up. So as a result, the next thing that will happen is that the cooler stuff that has come down will now become warmer. And having become warmer, it will also start to move up. And this will set you these convection rolls that you will see in a liquid. In fact, whenever you heat up a liquid, precisely for this very, very super simple reason, you have the convection rolls that come around and that ends up heating the entire liquid. But again, you'll always have more heat here than there, and therefore, if there is sufficient amount of material here, you will always see these convection rolls coming into play and being there. Now, as I mentioned briefly, this, for example, is the big reason why summertime some areas get certain kinds of winds. Santa Ana winds, for example. These are all ultimately dictated by various kind of convection rolls that are coming along. Some of it also happens in more heavy material, even colloidal material, where you can have liquids and solid particles, and you can do experiments to see these studies. And I can tell you that these experiments actually are not simple to do. They're rather difficult to do. So convection, for that reason, is mostly reserved for liquids and gases, because whatever stuff convection happens in, it must be happening in such a way that the material has a lot of, the atoms and molecules in the material inside has a lot of mobility. Because if it doesn't have the mobility, it cannot move around across large length scales and set up these convection rolls that you should see in a convection pattern. Oceans, for example, have that a lot, right? Because surface of the ocean becomes warmer, deep down it may be cooler, the warmer is lighter, the cooler is heavier, So ocean temperatures and how they vary can play a role. If you have seismic activity underneath the oceans, then it becomes hotter below, which means that stuff will rise up, stuff above will go down, that will set up convection rolls and currents and large waves and all kinds of. If you look at the stuff that's happening in Hawaii, the Kilauea, and if you look at the waves around, you know what's happening. Hot lava is falling, and that is really having an effect on the waves. In fact, I was looking at a video of that yesterday, and the waves were really, really interesting as they were running into the cliffs. It seemed fascinating that that enormous amount of heat was strongly affecting its behavior, the behavior of the water surface of the Pacific Ocean. The next thing I want to briefly discuss, let me go to another board because I probably should use up a little bit of space for that, is radiation. Radiation is probably the more complicated one at some level of these three. And radiation happens all the time, everywhere. So, radiation, therefore, is something that is omnipresent, if you will. And the way we think about radiation is as follows. Suppose we have an object that has a higher temperature than another object. Let's say I have some other object here. And let's say the temperature of this object is some high temperature T high, and the temperature of this object is some cooler temperature T cold. Okay? So let us say there is no atmosphere or anything, they are both in vacuum, so that you cannot have any conduction, because conduction requires the energy to be traveling through the material. If you don't have any material, you can't have any conduction. You can't have any convection because whatever fluid could have moved to conduct the heat is also not there because they are sitting in vacuum. So the question can now be asked as to whether there can be any energy transfer from here to there. Right? That's the question. And the answer is yes. And that is via radiation. The same way, for example, that sitting on Earth, we are able to exist because solar radiation is what gives us the heat energy that we need, other than whatever Earth gives us, to be able to have a functioning atmosphere capable of supporting life. Right? That's because of solar radiation largely. So it turns out then that even through vacuum, heat can go from one point to the other. And this is basically, this radiation is similar to, in fact it's physically the same as light radiation. Okay? So just like you see the sun, the light from the sun, the solar radiation that we get is essentially the same thing, excepting it's not in the visible part of the spectrum for us to be able to see it. We can't see that heat radiation is coming and hitting our body. We can't see that. We can feel it maybe because we may get a burn in our skin, but we can't really see it because our eyes are not designed to be able to determine that heat radiation, to be able to see that heat radiation in the way they are designed. So, but one can use thermal cameras, for example, to see some of their effects perhaps. But at any rate, radiation is something that is therefore invisible because our eyes are not designed to see them, but it's just like light. It can travel through vacuum. It travels at the same speed, the speed of light. It doesn't have the same wavelength as light, and that's the reason why we don't get to see it. But nevertheless, it's coming from a hot object to a cold object. And a common example would be from sun to earth. But then again, radiation is everywhere, right? I myself am radiating heat that you should be able to ideally figure out and receive. And you're doing just the same thing. So radiation is omnipresent, as I said. Radiation, the heat radiation, is actually a fairly complicated thing to study. And much of this work was done in the early 1900s by Max Planck and people like that, the early forefathers of quantum theory. Because light is a highly quantum mechanical entity at the end of the day, and some amount of quantum mechanics enters into this, although this is not something that we worry about right now. But the formula that you get at the end of the day is very interesting. The amount of heat that is put out by a body depends upon the absolute temperature of the body. But guess what? Strange enough, it depends upon the 4th power of the absolute temperature of the body. So, and that comes from the nature of the radiation. So in my graduate statistical physics class, for example, I actually do a calculation that gets into how this comes around by looking at various wavelengths in which radiation is coming and how it turns out they are distributed from the object itself. It depends upon the cross-sectional area of the mirror. It also depends upon a universal constant denoted by sigma. This sigma is called Stefan's constant. And Stefan's constant has a value which is the same everywhere in the universe. It's 5.67 times 10 to the minus 8 watts per meter square per Kelvin to the power 4. They're funky units because of the way these formulas are. And then there is another constant, E. So sigma therefore is Stefan's constant, and this E is called emissivity. So in this case, for example, what we'll have is we'll have H is equal to cross-sectional area involved, area involved, E sigma, but it will be T hot to the 4 minus T cold to the 4, because don't forget, it's not just T hot that's giving out radiation, T cold is as well, right? So therefore, both the temperatures come in the following way. But if you don't have anything, you just have a hot object sitting in space, that will also be emitting, and its absolute temperature T comes in. So let me tell you a little bit about emissivity. So what does E equal to 1 mean? E equal to 1 will happen from a perfectly black object. Okay? So black objects are very special. So when you wear black, I'm not wearing black today, but some of you are, that's a very special color for the following reason. Black, the reason why black is black as interpreted by our eyes is because all wavelengths of light are absorbed by black. So we don't see any color. Everything is absorbed. It's completely sucked up by the color black. So by the same token, because it takes in all wavelengths, and hence we don't see any color at all, which turns out our eye interprets it as black. Now you can imagine somebody else may not really look at your black shirt and think you're wearing black if their eyes are not made the same way as your and my eyes are, right? Because it depends upon the properties of our eyes that we see the black as black. It's relative in a way. But anyway, black also can emit all wavelengths, and that's why it's a perfect emitter. The E equal to 1 physically means that black as a color, or a black body as an object with that color can absorb radiation from all wavelengths, and it can also emit radiation from all wavelengths. So therefore, when you wear black, you tend to absorb some heat as well, right? Because all the radiation is being affected. But you are also an emitter. So at the end of the day, how much heat you retain is not trivial to compute. So at any rate, that's what we do regarding conduction, convection, and radiation. And I will try to give you some problems this Wednesday on these conduction, convection, and radiation business. There is a little bit more that I have to do, which I will do on Thursday, but let me just point out that when you have, since we are talking about heat energy, and I didn't really tell you a great deal about heat energy, heat energy is something very important because you probably know that there was something called the Industrial Revolution back in the 1700s, right? Industrial Revolution was a very important thing for humankind in a way, because it gave us, in the modern day, it gave us engines. It gave us the ability to do work with machines. And the idea of the Industrial Revolution is tied to the first law of thermodynamics. And the first law of thermodynamics has a very interesting and very simple form. It's an energy conservation law, actually. And it tells you that if you, let's say, give something an amount of heat delta Q, two things happen. First, one thing that can happen is that its internal energy can go up. So internal energy going up typically turns out to be dependent upon the temperature involved. There is a temperature change that can happen. And second, the material to which you have given the heat energy can actually do something for you, and that is work. Delta W is work. So you have given a gas, let's say, a certain amount of heat. The gas becomes hotter, so that will be delta U, internal energy change. And the hot gas can push something, meaning it can do work. Okay? So this is the concept of the first law of thermodynamics, and the reason why steam engines were developed, but because of one of the simplest possible applications of the first law of thermodynamics, because essentially steam, hot gas, hot vapor, the amount of heat you gave through cold burning or whatever is the delta Q. The temperature of the liquid went up, that was delta U, and the hot liquid can push something and hence do work, which can be used appropriately to, for example, it was used to design the steam engine by James Watts, hence the name Watts that we see everywhere. The reverse of this, where you can actually do the very opposite of it, is actually what a refrigerator is. So I'll try to tell you a little bit about the refrigerator next time as we finish, because everybody almost has a refrigerator nearby. But a refrigerator is also something that comes around because of first law of thermodynamics and another law, which I probably won't get into, but I can give you a flavor of that. All right, let's go to the quiz now.